20 meters in. Here. So, everybody, welcome to the February. Yeah, it's going to be March already. February presentation meeting for YCARS. I'm John Gendron NJ4Z. I'm the club trustee and one of the antenna geeks that hangs around the club. So, a lot of you may have seen some of these presentations. I've done this once or twice. I try to do it once every couple of years for the club on antenna modeling. So, there's several pieces of software out there. The one I'm most familiar with and probably the easiest to learn on is something called MMANA. That's Mike Alpha November Alpha. Um, and I sent out an email with links to where you can download it if you would so desire to do that. Um, there's also a piece of software called EasyNEC. There's another one called SimNEC. There's one called 4NEC2. They're all a little more advanced. Now, MMANA has a pro version you could pay for. They're still doing development on that. The free version hasn't had development done probably in about 8 or 9 years, but it's still a good piece of software for doing basic stuff. If you're going to do some really, really complex modeling, I'd suggest you look at Easy NEC or SimNEC. I'm still learning SimNEC. It's a new one for me. It takes time to learn these programs in order to teach people how to use them. And I'm still learning SimNEC, and the problem is I'm so used to MMA&A, I fall back to that versus trying to struggle with something I'm still learning to do some modeling. So what we're going to do is we're going to start out with some basic antennas, how to use the software, how to set it up, those kind of things. And as we get further down the rabbit hole, if you guys want to throw out some ideas about want to see some things modeled, we'd be glad to do that. So why do you want to use antenna software, right? One of the things is you want to learn how antennas work. Okay. So you want to see, where the current is distributed on an antenna, why the antenna is resonant, what, where in the band is it resonant? How does the SWR curve look for the antenna? All those kind of things without having to actually physically have an antenna there. It also gives you a chance to try it before you build it. So you can design something in the software. It doesn't cost you any money to do that. And then, once you get a result you like, then you can go ahead and um, uh, build it, and then test it against your design parameters, right? And see how the real world compares to your results out in the software. Um, Refining a design. Say you've got something that you've built and it's not doing what you want it to do. You can put the parameters in the software and see what it's actually doing, from an RF pattern, from a resonance standpoint, where the current is on the antenna wires, okay, or on the metal of the antennas. And the other part of it is once you figure out how these things work, it's fun just to sometimes play around with ideas, right? I've come up with a couple pretty cool antenna designs just playing around with the software, just coming up with ideas in my head saying, hey, will this work? And sure enough, it works. And I've built them and they work pretty well. So that's the reasons why you'd want to use antenna software. Again, it's for me, it's fun, and I like to stay on top of things and try to experiment. The one thing I said when I got into ham radio is I wasn't going to build my own antennas. I was just going to buy things. And, 7 years down the road, I'm actually starting to build and sell antennas. So, who go figure? Best laid plans, right? So I'm going to go ahead and share my screen. First, I'm going to move you guys from one monitor over to another monitor here. So I apologize for me looking to my right over here, but you guys are now on that screen, and I'm going to bring up the antenna modeling software, and I'm going to go ahead and share that screen. So, yeah, all right, so let me get my screen up here. It is screen number 3. Share. So you should see a axis here, X, Y, and Z. Everybody see that? Hello? Am
Yep,
I on?
I got
Okay.
it.
Okay.
See
All
it?
right.
We all
Yep.
muted.
Okay. So this is basically your design space. You've got four tabs up here. One is geometry. Two is view. This is where you can view what the antenna really looks like in space. This is your calculate screen. This is what does your heavy lifting for you. And then you have something called far field plots, and that's going to show you what your radiation pattern will look like from a top-down view and then from an elevation view. So we call this the plan view over here, and we call this the elevation view. There's also something called 3D FF, which is your 3D far field. It'll show you what your radiation pattern looks like in 3D. We also have your vertical field, your horizontal field, your total field, and then your H and F field combined. So those we'll get into. It's just if you've got a vertically polarized and you just want to look at the vertical polarization, you can look at the radiation pattern with just the vertical, just the horizontal, the total radiation pattern, or just the vertical and the horizontal, not any kind of variation in between that. Okay. Let me go back to the geometry screen. Okay, so geometry is a way of building the antenna without drawing it. Okay, so if I kind of know the parameters of an antenna and I want to build it, let's just do something simple here. So you're going to put in your X and Y Z coordinates for each wire in the antenna or each piece of the antenna, and you're going to do it in meters. So let's just do a simple vertical real quick. So I want to put it right dead center of the XY uh, axis. So my zero coordinate at X, I'm going to tab over my zero coordinate at Y, and then I'm going to put this thing on the ground because it's ground mounted vertical. That's a zero at Z. So Z is your vertical axis. And then I go to my second coordinate, which is the other end of the wire, okay, or the other end of the piece of metal, whatever you're going to use. So because I want a straight up and down vertical, that's going to be a zero there. It's going to be a zero on Y. And let's say we want to do this for, what do you say, 20 meters, okay? Um, if you use the antenna formula, and again, remember, this this program wants things in meters, not feet. So we're going to use one of two formulas. I'm a little more exacting. So most people use 300 divided by the megahertz frequency you want to target for. I use 299.8. So if we go 299.8 and we divide that by 14 1 or dot 175, which is the center of the 20 meter band, that gives me 21.15 meters. And we're going to take a quarter of that for a quarter wave vertical. So we divide that by four, and it gives us 5.287. So let's just call it 5.29. So I enter in here 5.29, 5.29, not 59 meters. Okay. And that's going to now, oh, I didn't tab it. 5.29. This thing's funny. It likes tab and not enter. This R here is the radius of the wire or the pipe, whatever you're going to use to build the antenna. So right now, zero point 0.8 millimeters in diameter is about a 20 millimeter wire. Sorry, not a 20 millimeter wire. Excuse me. It's a 20 gauge wire. We can take this up to 1 gauge or 1 millimeter, which is about an 18 gauge. And that's typically what I build my antennas in. Okay. If we go to the view tab, we're going to see our antenna. Okay. You can zoom in and out on it here. Okay. So there's our vertical. It's just a straight piece of wire from the ground up to 5.27 meters. Okay. If you want to change it, you can click on it. And then you come up here to the top, and there's a little thing that looks like an eraser. Okay. If you go there, it gives you the X, Y, Z axis, and then it gives you some choices here, right? So it shows us wire one starts at zero, right? 0, 0, 0, 0, 0, and then it continues to 0, 0, 5.29. So again, we're going straight up. The length of the segment's 5.29 meters. Okay. If I want to change it, I can look at the the projection in X and Y, and it's going to show me looking down. See that little red dot there is basically my antenna standing up. Okay. If I look at it in XZ, it's going to show me the antenna vertically in X and Z. Okay, so Z and X is running this way. If I go to YZ, it's going to present me the same model. Okay, so those are your three, and you got to remember you're thinking in three dimensionals here. Okay, if I wanted to change this, I can grab this point here by clicking on it, and I can rotate it. And this is in the XY portion. So if I move it to here, let's 5 point, let's put it right here. That's pretty close to what we have, but now it's sloping. If I say okay there and see how it's sloping now in the view, if I go to geometry, it's changed. It's 0, 0, 0, same origin point, but now I'm 4.2 meters in the Y and only 3.2 meters in the Z. Does that make sense to everybody? Okay. All right, great.
Yeah.
If you open up your mics and, I don't mind if people have open mics when we're doing this so you can ask questions. So feel free to
Open
do
mic
that.
night.
Yeah. Again, so while we're here, we do have this frequency here. This is your design frequency. So if you set it for 1.14175 megahertz, which is where we're working at, okay, that'll keep you straight. Now I'm going to go ahead and change this back to what we had originally. So I'm going to set that to a 0. I'm going to tab over, and we had 5.2. What was it? 5.2, 5.29, right? Yeah. Okay, 5.29. Now, that's just the wire. We have to have a feed point for this thing. Okay. So there's a couple ways to enter a feed point. I can enter a feed point down here where it says source. Okay. If I click on this and I type in wire one, so that's W1, and then do I want to feed it at the beginning, the end, or the center? Okay. Since this is a ground mount vertical and we have our X, Y, and Z at 0, that's our beginning point. I'm going to feed it at the beginning. So that's W1B. So wire one beginning. Okay. And I hit the tab button. Now you can change this voltage. That's really more an advanced thing. I wouldn't worry about it. And phasing degrees, don't worry about that right now. We're not going down that road. But this is where you would change, if you were doing an array, you would change the phase here at feed points and be able to give you your pattern, change your pattern. The loads also will give, you can put in a load for a coil or a capacitor to give you some changes to balance your antenna. So if you want to do a coil loaded 80 meter vertical, you can load in a coil, but we're gonna go down that road just yet. We want to get the basics down first. So right now, if we go back to our view, now we have the wire, and you see the red circle down here at the bottom of the wire? That is our feed point. Okay. So now we've got a piece of coax attached to that wire. Okay. If we go to the calculate board here, this is where we're going to uh, use our frequency that we want to target. So 14.175 megahertz. We're going to use ground. You can put it in free space. You can put it over perfect ground, and you can use real. Always try to use the real ground. Okay. And you set this ground setup. Okay. For most of the soil in this area of our part of the Carolinas, our dielectric in the soil, our conductivity dielectric in the soil is about 13. Some places it's 14, some places it's 12. So a generic number of 13 works really, really well. And you can pull down a map of the United States and see these soil conditions. I'll have to get you guys the link. I don't know it off the top of my head right now. And then you have the conductivity of soil in millisiemens per meter. Okay. Around here, it's about 5 millisiemens per meter. If you're closer to coast, the closer you get to salt water, the higher this number goes up. Okay. So if you're sitting on the beach in Myrtle Beach, your dielectric's probably still about 13, but this is about 1,000 times higher, right? You're going to be about 5,000 millisiemens per meter. Okay. And that has some real effect on your transmission pattern and your gain of your antenna. Okay, we'll play with that a little bit later, but just for right now, for our area, Rock Hill area, York County, Charlotte area, we're looking at 13 and 5 in these boxes. Don't worry about the R. Don't worry about the height. We're not going to do
Is
anything
that
with that tonight.
does
Okay. Okay.
that those numbers like the conductivity in it, does that matter how far you are off the away from the ground?
It no, it's just it's ground connectivity, right?
Okay,
So ground mounted it's going to affect ground mounted elements and radial fields more than it will your dipoles that are high above the ground because you're not seeing that much ground loss or that much ground reflectivity the higher up you are. Does that make
right.
sense? Okay.
Yeah. I
Okay.
asked because I'm in a three-story here.
Yeah, no, I
This
got you.
one starts up
Right.
higher.
You're not going to ground mount anything in a three-story, I don't think, right? No. Okay. Um, so, and then we're going to talk about radials. Okay. So on the bottom here, you're going to have, you can turn on and off radials. Okay. For me, I'm going to put down typically 8 radials with the same kind of wire that I've got on the antenna. So we'll make that 1 millimeter. Um, and we'll put them out and around. Okay. So those are going to be quarter wave verticals for the antenna I'm building for the frequency I'm using. Okay. So that's our ground setup. Once you build your antenna, you can add additional height. So if you when we get into building dipoles or inverted V's or loops, we'll show you how to build them, and then you can add height to them to change them, right? With a ground mounted vertical right now, we're not worried about that. And then you have your material. So you have copper wire, copper pipe, aluminum wire, aluminum pipe, iron wire, iron or steel, and then you can define some wire if you want to. For right now, we're going to use copper wire. Pipe, you have to draw different segments and change the diameter of the pipe if the diameter of the pipe changes, because with diameter of your conductor, that changes the bandwidth of your antenna. Okay. The larger the diameter, the larger your usable bandwidth will be for your SWR curves. Okay. It has to do with skin effect of and how RF flows on the outside of the surface of the material that's making up the antenna. Okay. So when we're talking about RF in with a wire antenna, that RF is typically not flowing up the center of the wire, it's flowing on the outside of the wire. Okay. So it's eddy currents and skin effect is that RF is traveling up the wire and it's not going up inside the wire. Okay. So just understand what we're dealing with there. Okay. So now we've got the frequency we want, we got our ground set up, we got our material set up, we've got our height set up. Okay. We have the frequency set in there, so we're going to hit the start button. Okay. So now it puts a result out. It gives us our frequency, it gives us our real resistance in ohms. Okay. So it's saying we're looking at 40.25 ohms of pure resistance. That's resistivity. Then we have our reactive component, which is 22.9. So we got 22.9 ohms of reactivity. That's going to be capacitive reactance, not inductive reactance. And our SWR at 50 ohms is 1.73. Okay. And we have a dB gain of 0.54. And that elevation, that's the maximum dB gain. And that's dBi. That's against an isotropic um, radiator. So it's a theoretical single point of a sphere, single point with sphere radiation pattern. So it's just going to be against the unity gain antenna. Okay. So we get a little bit of gain at 27.3 degrees takeoff angle. Okay. And the pearl polarization is mostly vertical. So what does that tell us? Well, we can take a look at the far field plots of the antenna. So here we go. All right. Looking down, it looks like a big old circle. Okay. If you cut that circle in half, looking at it from the side, you're going to see a kind of almost a butterfly shape. Okay. In 3D, it's going to look like a donut. Okay. So we got a big old hole right here through the center where the radiator is, and then all your RF is listed on the outside. You can see your scale, right? Negative 30 dBs is dark blue. And then as you go up the scale to pink, it goes to 0 dB of gain. Okay. Now you can do some, again, you can look at the vertical field, doesn't change. Horizontal field, because it's a vertical antenna, there is no horizontal field. And then I can look at the total field. If I want to zoom it in, I can zoom in, I can zoom out on this. Okay. You can also save this if you want to save it. You can save it as a PDF file. Okay. So you would click save image and it'll pull up and you just put it where what file you want to put it as in what directory on your computer. Okay. What does this information give us? Well, this shows us that we have an omnidirectional pattern. Okay. And I apologize. My computer, the monitor I'm showing this on to you on, actually is a little out of um, not scale, but it's not perfectly square, so it's going to look a little more oblong than it really is. This is a circular pattern if you look at it. Okay, it's the scale's wrong on here because of the way the monitors. It's a really widescreen monitor. It's a 39-inch monitor. So, but you can rotate this around, and you can see as I'm looking at degrees up here, my azimuth is changing. So this is my degrees in azimuth along, um, you know, say this was north, then it's northeast. Come on, let's not play around here. Northeast, then I go around to south. I'm having trouble with my mouse tonight. South, come on, west, and back to north. Okay. So it's varying degrees, but it's showing me what my dB gain is. So it's here, it's 0.5 dBi over an isotropic. I can do the same thing over here. I can rotate it. This is your elevation. Okay. So here I'm at 0 degrees. As I go up, I'm climbing. So here I'm at about 3 degrees off the horizon. Here I'm at about 20 degrees off the horizon. Here I'm at 30 degrees off the horizon. Your horizon's at 180 degrees and your vertical's at 0 degrees or 90 degrees. I'm sorry. And you come along here. So that's what your RF pattern looks like. And you can see your gain anywhere along the RF pattern. Now, if you want to change and look at a specific point and see what this pattern looks at, let's say 10 degrees. Okay. So here's 180 degrees. So 180. So I'm going to go to 170. And this is showing me I have a gain of negative 2.3 dBi. I can go here to elevation and I could change this from 27.3, which is our maximum, to 10. And there's the pattern at 10 degrees. Okay. Does that make sense to y'all? Okay. Now I'm going to go back to the calculate center here. Okay. There's some buttons here along the bottom that show our plots. Okay. So if you hit this plot button, I can look at my impedance directly. Okay. That's not only my resistive, but it's also my reactance in the antenna system. I can look at my SWR curve. I can look at my front to back gain, which this has no front to back gain because it's omnidirectional. I can look at my far field plots, right? And then I can look at my setup. If I want to change my SWR, I can change what my limits are to accept what it is. I can also change my bandwidth up here. So the 20-meter band is 14 megahertz up to 14,350. So if I'm dead center of the band and I choose 400, I'm going to do 200 on either side. So I'm going to encompass the whole band if I look at SWR for this, right? So let's say I want to look at detailed SWR for a bandwidth of 400 kilohertz across the 20-meter band, and I hit it. Okay, so there's my SWR. I'm at 1.5, just below 1.5 here at the low end of the band. And at the high end of the band, I'm over 2.0. Okay. What does that tell us about this antenna?
It's too
Anybody know?
long.
Yeah, too long. So if I want to widen this up and see kind of where I'm too long at, now look, my resonant points way down here. I'm dropping SWR down here at 13.17775. If I take this out a little bit further and go detailed, all right, so it looks like it bottoms out somewhere around 13.675. So this antenna is pretty long for what we want to look
Mm.
at. If we want to see where it's resonant at, right, we can see it's resonant somewhere down here at the bottom. Resonance point is, let's see, it's easier to do it this way. Resonant points where it crosses zero here. So that antenna is resonant at 13.751 megahertz. So we know the antenna is a little bit long. And you can also print these results if you want to. So let's go ahead and change the antenna a little bit, right? So we know it's long. Let's take it down to 5 point, let's take quarter of a meter out of it, okay? So we were 5.29, let's go 5.04, right? And now we'll hit calculate again. And if I can see there we go, start button. Oh, my SWR came down a little bit. My resistance came down a little bit. And instead of being capacitive, now I'm inductive reactance in the setup. So if I go to my plots now, and I go to my SWR plot for 400, and we go detailed, guess what? Now I'm short. So they have a button on here called optimize. And where is it at?
Bottom of the,
Optimization, right?
Yeah.
To hit that button, and we're going to go for, we want SWR and the match here. And I'm going to go all elements. And we're going to let it go ahead and do that. And we go start. And it's going to run a bunch of calculations. And it's going to give us a new geometry. Why is it dinging at me here? I don't know why it's dinging at me. Oh, because it wants me to save the log. I see it's over here. It popped up in a different screen. Okay, so now I go at my geometry, and it's got me at 5.14. Okay, so that's where this antenna is going to be optimized at. So now if I go back to my calculate screen, we run it again. And now my SWR is 1.36. Okay. Now you say, why can't we get any better than 1.36? Well, because the inherent um, impedance of a ground mounted vertical, for the most part, is going to be right around 35 to 36 ohms. Okay. So where are we at? 36.68 ohms. It's got very little reactance in the system, right? So if we look at the plot here and we do SWR now and we hit detailed, there's our lowest point right where we wanted it. Okay. And if you look at the SWR curve, what happened here? We were at 2 on one, we were 2 over here on the other on the low side. Now all of a sudden, where are we at? We're below 1.5 all the way across the band, right?
Mhm.
So we've optimized that antenna. Now, the interesting thing is, again, we were talking about this. If I go to my geometry and I make this, let's make this, I don't know, 5 millimeters. All right. So we're going to change the diameter of that wire. Now, I've got pretty big wire going here. It's probably going to change the SWR a little bit, and it's probably going to change the length of the antenna just a little bit. Yeah, a little bit different. And the impedance went up just a little bit, but look at the SWR curve now. That SWR curve's down. See how it came down, right? It dropped way down from where it was at. It was almost 0.1 in the match, where we were above 1.5 here. Now we're below or just above 1.4. Okay. So again, diameter does play a part in your bandwidth on your antenna. Okay. So when we were creeping up over getting close to 1.6, 1.7 here, it dropped it down. Um, so it's just something to think about when you're thinking about building antennas. The bigger the wire you use, the better your bandwidth is going to, usable bandwidth of that thing is going to be for your SWR curve. That being said, the bigger diameter you get, the heavier that antenna is going to be. So it's a trade-off. Everything's a compromise, right? You get better response from the antenna with a thicker wire, but you give up the weight factor. That's why a lot of times if you see a really long 80 meter, like an 80 or 160-meter dipole, you'll see them drawn out. You'll see them built where there's several wires and they're all circular. So you'll have a couple of plates in the antenna itself. The feed point will be a single point. You'll have 6 or 8 wires coming out, and they'll be through those plates, and you'll end up looking like a barrel of wire. And then at the ends, they all come back together. And what they're doing is they're broadbanding that antenna. So they're adding more surface area by adding wire instead of making the center conductor thicker. They're adding more wire so that when that energy comes out, it spreads around all of those 6 or 8 wires, and it gives you better frequency response so that they can open up that bandwidth on that antenna. It's called a cage antenna. So if you've ever seen a cage, and I've actually experimented with that and built an 80-meter vertical using 5 elements, 6 elements, and brought it up and it widebanded it. So instead of just having like 50 kc of running operation, I can pull it out to about 150 kc doing it that way. So it helps you with your SWR usable SWR curve of the antenna. Um, let's talk about dipoles.
Hey,
Everybody,
John,
yes,
John, before you go on that calculate screen, do
yes.
you know if there's a way to clear those results at the bottom to start over, or do you have to close out every time?
That's a good question. I typically just leave them up there because a lot of times I'm referring back and forth between them. But when you start a new file, it will blow it out, right? I
Yeah,
don't know if I never looked to clear it, to be
I've
honest
never
with you.
figured out a way to do it.
Yeah,
I
I don't know
can't
if
find
there's
a
a way.
way.
Yeah, I mean, if you do it, if you go to new, right? And I'm not going to save that vertical. Um, and I start with geometry again. I don't know. It should. Let me see if I do this. Let's do a 40-meter one just for
No, I
giggles
think it
here.
leaves them in there.
10.25. Let's see what happens. Calculate. Oh, I didn't put a feed point in there. Wire one base. Calculate. No, it leaves them in there, doesn't it? Yeah. So, well, I didn't
Is
put
it
the right
just reading a
frequency.
text file when you save the log?
Yeah, I think that's what it's doing.
Yeah. So you
Yeah.
could probably find the text file and
And
blow
just
it up.
blow it out. Yeah. Um,
Or just close it and start again.
close it, start again. Yeah. It doesn't bother me to have all that data up there again. Usually if I'm doing it, I'm only working on one antenna. I don't switch back and forth a whole bunch unless I'm building something for like a presentation where I'm doing a bunch of different antennas for people. Anyways, it gets to a point eventually if you're not good at doing the math in your head and you're not used to coordinates, if we go back to the view, let's do a new here and we'll clear this. No. All right, so I got a clear screen here. If I go up here and hit that eraser again up here on the top, it gives me my screen, my view screen, right? If I want to draw, let's do a dipole, right? So I'm going to go to X and Y, and I'm going to go over here to the pencil, and I'm going to click the pencil. 20-meter well, let's do a 40-meter dipole. So, let's see. I'm just using my calculator here on the other screen. So 299.8 divided by 7.150, which is the center of the 40-meter band. That gives us 41.93. Okay. Now, with a flat top dipole, it's a half wave, right? So if I divide by 2, That'll give me my half wavelength. That's 20.96, 20.97. Okay. So I'm going to go along the x-axis here and I'm going to start drawing. And I'm going to come, let's say I want 3 boxes. So let's do 3 boxes over here. All right. My length of that wire is 70 meters. That's way too long. So let me grab it. Let's see. Escape. Whoops. Didn't mean to do that. Sorry about that, folks. Confusing 2 programs here. All right. So let me draw this again. So let's see. Let's start here. Get the pencil. Start here. Let's go this box to this box. Okay, that's 40 meters. What's my scale here? So my scale basically is each box is about 10 meters. So I'm going to go back here to the eraser and I'm going to grab this point and I'm going to bring it back here.
Also, if you look in the upper right, it shows you how many meters over you are.
Yeah, that's what I was going to say. So here up in this point, it shows I'm at 20 meters here. Okay.
Yeah, but below that, when you were drawing, it
Oh,
shows
did
the
it
X and
really?
Y.
Oh,
Yeah,
I didn't notice that. So thank you, Danny.
yeah.
So I'm going to zoom this up just a little bit. And now it's going to give me a little bit of more flexibility to pull this out just a hair. So I'm going to move this. I need 20.97 meters. So I'm going to pull this out here. And that gives me 20.5. This gives me 20. That'll give me about 21 meters. Close enough for what we're going to do right now. So I'm going to hit OK. And it's going to show me my dipole on the bottom. Now, in order to build a source in it from here, from this screen, if I right click, it's going to give me add move source here. And I can add it to the center of the wire, beginning of the wire, end of the wire. Okay. And it always says not recommended beginning or end, even though you have end feds and verticals and everything else. Right. But since we have a 21-meter wire and we're building a 40-meter dipole, we want to feed this thing in the center. So we'll put a center. And magically, my little dot appears here in the center. Okay. Does that make sense to everybody?
Yep.
Okay.
Yep.
So now, if we go to the geometry screen, I'm going to change this to be 7.150 megahertz, because that's what we're designing this antenna for. And it shows me I'm at X minus 10.5, 0, 0. Y and Z are 0 because I'm on the ground and my Y is, I'm drawing along the X axis. And here I have 10.5. So 10, negative 10.5 to 10.5 is 21 meters. Okay. Does that make sense to everybody?
Yep.
All right. And I'm going to change this to to 1 again. And I'm going to have wire 1 fed in the center. Okay. So if I go to my calculate screen, it comes up. I'm at 7.15 megahertz. You know what? I don't need radials on this thing because it's a dipole. So I'm going to turn off the radials. And now I'm going to add some height to it. So let's say we put it at 10 meters, so at 30 feet. That's most people get an antenna up 30 feet, right? And we're going to flat top it. So we're going to have it fed at 30 feet and 30 feet at both sides. Okay. And we're going to use copper wire again. And we're going to go ahead and hit start and calculate this thing. All right. So we got 93.99 ohms, 82.7 ohms of capacitive reactance, and we got an SWR of 3.57. Well, that doesn't look like it works pretty well, right? So why are we getting that? Well, because the antenna is pretty close to the ground. Okay, so this capacitance is being added by the ground. Okay, to our system. That's why the SWR is off. Also, we're looking for a 50 ohm load, and we got 93.99 ohms of resistivity here, right? So real resistance. Well, typically a dipole, have center fed dipole, is inherently around 72 ohms. So you're going to see an SWR typically about 1.5 if you're dead on it. Okay. So let's look at the plots and see what we're looking at again. So now we're in the 40-meter band, our SWR. Let's find out if we're long, short, whatever. So we have 300. Basically, our band is from 7 to 7.3. So if I put 350 in here for the bandwidth for kilohertz, it gives me a range of 6.95 just below the band and to 7.325 just above the band. And I hit a detail. And boy, guess what? We're long again. Okay. Now, the reason we're long is because we're closer to the ground. Okay. Now, there's two things. If I can only get this antenna up 30 feet, I need to shorten it. If I can get it up higher, then I may not have to shorten it. Okay. This is where the compromise comes in for what you can do in height. Okay. So let's say I can get it up to 45 feet. So I'm going to get 15 meters now. I got bigger trees than I had before. Okay. Hit start. Now my SWR came down. My resistance went up a little bit. My capacitance came down, and I'm at 2.57 in my SWR. So if I plot this again, you'll see this thing should have shortened up some by going up higher. So detailed. Yep, it shortened up some. So let's go ahead and shorten the antenna a little bit, or let's run the optimization on it and just let the optimizer do it. Right? Why do the work if we're just going to let it do it? So all elements start. Okay, so what did it give us now? Geometry. Oh, I don't want to save this stupid thing. Cancel. Okay. Geometry. So it gave us 10.22 and 10.22. Made it longer. That's weird. Okay. What's my SWR look like now? 1.98. So it brought it down. That's weird. The SWR, that resistance doesn't look right to me. All right. Well, let's look at the field for our field plot. Again, looking down on it, it kind of gives us a kind of a bowed shape. If you can see along the x-axis where the antenna is, the antenna rides this way. You can see it's a little bit narrower here, but it comes out further here. So we're getting an egg shape. So we're going broadside off that antenna. And because we're so close to the ground, it's pushing most of the RF up. So our maximum gain is at 74 degrees, right? What does it look like in 3D, which is useful for us to look at? There's our 3D look at this thing, okay? So the antenna is along this x-axis. You can see it. It's sitting right on the axis, okay? So it's a little hard to see, but it's that black line. But that's what your RF pattern looks like. So if this is your antenna here, you're broadside. So if this is facing north-south, you're pushing out your RF east-west. Does that make sense to you? Okay.
Yeah.
Yep.
We'll close out of that. Okay. Now, let's say we got some really big trees. Okay. We're going to push this thing up to, let's say we can get it 60 feet in the air. And we'll go ahead and hit it. Now my SWR is more reasonable, right? We're at 1.6. And our far field plot should be a little different. Look at the far field plot now, right? That big bubble RF we had, all of a sudden it's pushed out. And our maximum now is at 43 degrees instead of 74 degrees. Okay. So the lower that antenna gets to the ground, the more reflectivity you get off the ground, the more it pushes it up. So you end up with more of an NVES signal. Now you're going to start seeing some DX off of this thing, at least short DX, right? Maybe, what are we at? What are we, 43 degrees? Say your first hop's going to be about 250, 300 miles. Your second hop's going to be, maybe about 500. Your second hop's going to be about 1,000. So Europe's going to be coming in. It'll be a little weak to you, but you'll do okay. Um, let's look at it in 3D or this way. So our max gain, let's see, elevation, let's change it to 10 degrees. And you're 1.8 dB at 10 degrees. Okay. So a vertical at 10 degrees is typically about negative 2 dB. So you're going to be about 3 dB, 4 dB better with a dipole at 40 meters hung up this high than you would be off a vertical with that. But again, you're 66 feet in the air. All right. If you get an antenna up that great, the dipole is going to work better than a vertical for you in that case. Right. And that's good for that's a good angle for DX. Five degrees is really your long distance DX. And you're at
Five's the magic
3.7.
number.
What's that?
Five's the magic number.
Yeah, you hear people, and again, I'm gonna get a little bit in the weeds here, so I apologize, but you hear people talk about 5 degrees, and there's people who are proponents of 5 degrees, and there's people saying you never radiate 5 degrees because of ground losses. For a dipole, I think it's true. For a vertical, I think you really start seeing stuff at about 7. But I'm not going to argue that point. Everybody has their opinion on it. And again, if you get three hams in a room, you're going to get 4 opinions.
If you
So
shoot for 5, your 10 will be good.
yeah, exactly. So I'm negative 3.7. A standard vertical is going to be about negative 5.1. So you're still about 2 dB better here than you would be against a vertical. So about 60% more signal getting out versus a vertical antenna. But again, keep in mind, we're dealing with a lot of height here. If we
Hey,
take it,
John,
yes,
I'm sorry.
go
Now,
ahead.
are you also here? You're going to pick up more maybe unwanted noise from that dipole if
No,
you're
so
getting that much more angle or no?
the dipole is horizontal, right? Now, you can pick up noise horizontally, but most of your man-made noise has a vertical component to it.
Right.
Electrical transformers. So typically verticals are going to be more susceptible to noise than a dipole. A loop, because it's a closed system, is less susceptible to that stuff. Okay. So yeah, again, it's all trade-offs. But just say for fun, we can get this thing 90 feet up. We got some really tall pine trees, right? Now, look at my dB gain between this at 60 feet, okay? Negative 2.9, and look now at 6.46, okay? And let's look at my far field plots. We've got that big bubble RF. Now, granted, but this here is a pretty good pattern. Okay. Oh, we're at 5 degrees to elevation. Got my elevation back out to 10. There's my elevation at 10 degrees. Okay. 5 dB of elevation. If I go to 5 degrees, what do we have? Negative 2 point something, right? Now I'm at 1, negative 1. So I've picked up almost 3 dB here. Against a vertical, I'm 5 dB better. So I'm almost an S unit higher with this antenna but again, I'm at how high?
90
Calculate.
feet.
I'm at 90 feet. Okay. Versus a ground mounted vertical. Now, I don't know. People can hang things at 90 feet. And I've got some pine trees here that are about 75 feet tall, but getting it up that high is a challenge, right? But yeah, so height is might with a dipole. Okay. Does that make sense? All right.
Yep.
Let's look at another dipole here while we're looking at it. I'm going to change this. Let's start a new, no. Okay. So an off-center fed dipole. Okay. Typically 135 feet long for 10 through 80. And typically you see them fed at 135 at about 39 feet on one end. So that's going to give us what, 12? What's the math there? 6, about 96 on the other side. So I'm going to do 39 and 96. Let me do a couple quick calculations here to get my math to 39 is 11.89 meters. And my 96 feet is going to be 28.35 feet. Okay. Or meters. So I'm going to do this one real quick here. I'm going to do it X and Y. So 11.8900 and 000. And this one is going to be negative 28.35. 00000. Okay, so this should be a straight line when I look at it. View. Okay, so I got a straight line. I'm gonna feed the end of the wire. Yeah, so it came up in the center. So now I'm center feeding this. Okay. Now, typically with an off center fed dipole, what balun do you use with that if you want to feed it with coax? Anybody know?
4 to 1.
4 to 1. So if I've got a native impedance at 50 ohms, what my radio's looking for, and I'm using a 4 to 1 balun, what does that tell you my impedance should be at the feed point?
200.
Yep. So I'm going to come up here to center setup, and I'm going to click setup and see it says standard Z SWR equals 1. Let's change this to 200 for this one. Okay. So that takes into account I've got a 4 to 1 balun here now. Okay. So I got my transformer in place. And we're going to go to calculate. Let's bring this down to something reasonable. How
Not
about
90 feet anymore.
How about 15 meters? So about 45 feet. Okay. Excuse me. We'll check I'm sure my ground's off. Yep. Okay. And let's look at it at, I don't know, let's look at it at 40 meters for right now. Because this is a multi-banded antenna, right? So I'm going to look at it at 40 meters. I'm going to hit start. My SWR is 2.03. Okay. Which isn't crazy. Far field plot. Elevation. So at 52 degrees, I've got I got this weird peanut shape, right, or figure eight shape along the long axis. So I've got a null right in the center of the antenna, which you would think because of the way the antenna is constructed, okay, because you've got two pieces of wire. So your currents, if I look at the view of the antenna and I've got my currents turned on, if I look at where my currents are, okay, so my low current point is here, my high current point's here, another low current point, a high current point, a low current point. Okay. So if I turn that on its side, what does it look like?
Looks
Looks
like
like
that shape.
the RF pattern, right? Okay. So that's how you determine what your RF pattern is going to look like some of the time with a dipole, right? Um, and we really don't have any vertical component on this. It's all going to be horizontal components. So if we go back to our far field plots, if I go to my 3D plot, this will give you a little better feel for it. So you got like a butterfly there. Okay. Does that make sense to you?
Yep.
Along the broad side of the antenna? Because the
Yeah.
antenna's running this way. Okay. Now, that SWR isn't bad. We could play with the length of this and change it around a little bit. What you're looking for when you're building one of these antennas is you're looking to find a feed point where your currents are all close to a maximum. Okay. So for each band you want to feed. So let's take this down to 20, 14.175. And let's see what it looks like at 20 meters. My SWR is way off on 20 meters. Now, that's probably because I've got it fed weird. But let's look at the far field plot on this. And let's take it to 3D so we can see what it really looks like. Yeah. Okay. So because we've got some height above ground and we have um, multiple wavelengths here, you're starting to see multiple lobes. Okay. You got this lobe here in the center, which is NVES kind of propagation. And you've got these lobes out here on the side, which are lower angle radiation, and they're higher gains. So, and then you've got these secondary lobes off to the side here. Again, higher gain, little different elevation, little lower elevation there. So, um, this really doesn't do the pattern justice, but you can see you've got some, because we can't turn this thing really well. I don't think.
If you, I think you can rotate.
Yeah, you rotate it 90 degrees, but that's pretty
Yeah.
much it. Yeah. It doesn't really change your elevation, but see, you got one lobe out here where you got some gain there, you got some gain here at a different elevation. But you really want to look at 3D when you're looking at this, and it kind of gives you the feel for it where you have multiple lobes. Okay. If we look at this at 80, you're going to have one lobe. If you look at it at 40, it's the second harmonic. It's going to have two lobes. If you look at it at 20, it's the fourth harmonic. So you got four lobes out there, right? Or three lobes out there, excuse me. And so you end up with all your harmonics putting out
More of a
lobes.
mess the higher you go.
Yeah. So if I go now, we'll go to 15 meters, right? 21.200 for roundabout numbers. My SWR climbs again, far field plots. Now you can see what kind of craziness you got going on there. If we look at it 3D, right? There we go. So, and it's just a matter, if we look at the currents, we can probably figure a better place to feed this. So if I go over to view, now look at my currents there, right? I've got multiple wavelengths down here, right? Because that curve's going up, down, up, down, up, down, up, down, right? So we've got multiple wavelengths we're dealing with. What is it typically that people feed that thing? 45 and 90. So what's 45? 45 meters is 13.72, and 90 should be double that, right? 27.43. Okay, I'm gonna go in and change geometry real quick. And come on, mouse. I don't know whether my batteries are going low or I got something else going on with the darn mouse. 13 point. Why are you not letting me change this? I think my batteries are starting to die in my mouse. 13.72. All right. Is 0. And we've got 27, no, negative 27.43 here. Okay, view. All right, so this is a 4590, so it's fed 33% through it. And do our calculations now. And let's look at 40 again first. Come on, mouse. Oh, what this thing's doing here. Sorry about that, guys.
All right.
Okay, so our SWR came down. This is more like it. Okay, so let's look at our far field plot here. All right, now we're seeing that peanut shape again, 3D. Yeah, we got two lobes because that's a second fundamental or second harmonic. 80 meters is the fundamental on this antenna. So if we look at 80 meters, we'll only have one lobe out there. So if we go to our calculate screen and take this up to 80 meters, let's take a 3.6. I don't know if that may be a little short for that. Yeah, it's probably a little short for that. And there's our far field plot. So now we have, if we look at it, we've got one lobe, right? And it's NVES pretty much. Okay. So again, your harmonics, you're going to get lobes, number of lobes. So if I go to calculate now, I go down to 20. I should have 4 lobes on 20, right? Yes. So far field plots. Oh. Yep, 4 lobes. So that's where we're at. That makes sense to everybody?
Yes.
Okay, cool. And don't be afraid to ask questions. Stop me and just ask me questions. All right. So we talked about dipoles. We've talked about verticals. Walt was talking about loops. Okay. So with a loop, you can feed those a couple different ways. You can feed them with a 4-to-1 balun. You can feed them with a 2.5-to-1 balun. Difference is the length of the wire because that changes your impedance, right? Before we get into loops, let's look at end-fed dipole, end-fed half waves. Okay, just so we have that. So I'm gonna do a simple end-fed half wave. So let's do 299.8 divided by 7.150 target middle of 40-meter band. That's 41.93 divided by 2 is going to give us 20.97 meters. So I'm going to go file new. Yeah, no, I don't want to save changes. Okay, geometry. So we're going to start at, I want to do this as a sloper, so it's going to be easier to draw it. Okay. What's that? Oh, I thought somebody was calling me. They were calling net control. All right, X and Z. All right, so we're going to draw this in. We're going to start here in the center.
I'm going to be in and out, but I will be monitoring.
And let's go. What do we want? 20 point. We want almost 21 meters. So let's see. I'll put this thing right about here. I might have to zoom it in a little bit. That's not what I wanted to do. I want to move it. I'll grab it and move it to here. 21.4. What I want, just under 21. That's pretty close. Okay. So here's my half wave end fed antenna, right? Okay. So that's what it's going to look like. I got to go here and change the setup. So the half wave end fed, we just built one of these at the clubhouse. You feed it with a 49-to-1 balun. Okay. So 49 times 50 ohms is now 2,450 ohms, right? So that's what I'm trying to match here is 2,450. So go to my calculate, and we're going to take this down. We're going to put this on the ground, and let's look at it for 40 meters. Copper wire now. It has no source. Well, we need to put a source on this thing. Wire one beginning. Wire one beginning. Okay. Now we'll go back to calculate. All right. Now we hit the start button. And we have a 3.731 SWR because we got a lot of inductive reactance here because it's sitting so close to the ground. We can probably play around with the height above ground and change that just a little bit. And we could probably play with the length of the wire. But for right now, let's, we won't worry about that. But let's look at the far field plot on it. And it gives you kind of almost an omnidirectional pattern, but it's flattened on one side. You can see that here, right? As you're looking at it from the side. If I look at it from a 3D, right? And now, who would have thought it's going to radiate more off the back side of that antenna?
Yeah.
Right? Who would have thought that? But that's the way the radiation pattern plays. But a lot of these guys run a counterpoise with this antenna, right? So let's run a little bit of a counterpoise on it. About 17 feet is usually what they run. Let's do 17 feet. So it's about just over 5 meters. So let's go to geometry and we'll add another wire and we'll put it at 0, 0, 0, 0. Oh no, we're going to put it 5.18. And why is my Z's at 10? Okay, yeah, because I'm going up with a thing. All right, so now let's go to our calc. Let's go to our view. Now I got my little, whoops, got the counterpoise the wrong way. I need this at negative 5.18. Tab. There we go. Now it's opposite our feed point there. Okay, or opposite our wire. Now it's our calculations. Let's see if that helps with our capacitance. Why isn't it calculating? Calculate.
You're going to have to raise it just a little. You put that second wire right on the ground, it won't calculate. You'll have to raise it like 0.01 meter
Okay.
to get it to
Let's go.
calculate. So just adjust your Z on both of them to 0.01.
Damn it. 0.01 tab. 0.01
Not that one.
tab.
Go to the other one. Yeah, you can do it on
Uh,
all of them, but you'll need to do it on Z2 there.
Yeah, so I'm getting right down here.
Perfect.
0.01. And I need to do this at 0.01. Otherwise, it's going to add length to it.
Yep.
Okay. Now let's
That's
see
one of
what
the
happens.
things finicky about the program. It doesn't want to understand something could touch the ground.
Okay. So it really didn't make too much change. Let's see what it did to the far field plot. Nothing really. So, really didn't change much by putting that counterpoise on there. Yeah, about the same thing. So,
Did it bring the SWR down though?
uh,
It should have brought the SWR down some.
It looked the same, yeah.
yeah, well, it came down about half of it, and
Yeah.
we're probably a
Yeah.
little bit long. So, my guess is it probably needs to be shortened up a little bit. And if we bring it down to the ground a little bit, it'll add some capacitance to this. So it'll probably change it. If I change that view,
What's interesting is with that antenna, you could actually put radials down and you'll
Yeah.
see your SWR come down and it'll
Right.
change your pattern a bit.
yeah. So if I go here and change this, we want 20.59. Let's bring it down a little bit different angle here. So I'll bring it down to here. Okay. We brought it down a good bit. Now it's a flatter angle. Geometry. If I hit I don't want geometry, I want calculate. Darn it. Hit my start button. Yeah, there you go. All right. So it needed that capacitance in there. Now it's down 5.2. Far field plot shouldn't really change all that much. Okay. 3D. And there we go. Well, it picked up a little bit on the backside of it, right? So it operates a little better at a lower angle. Now, if we cut it a little bit shorter, it would probably work a little better. But that's where we're at now. Again, with this antenna, it's multi-banded. Excuse me. So if we look at 14.150 and calculate on there, no, I did that already. 7.15. Yeah, so we said we did it different. That's what we changed the frequency. That's why I changed. So if I go to 15 meters, far field plot. Yeah, see, I'm starting to get multiple lobes here on 15 meters. So yeah, that's kind of a nice pattern on 15 meters, actually.
Yeah, it is.
Yeah, that's actually kind of nice. I like that.
So with that, you can tell that you want to point it towards Europe, and then on the backside, you might get South America.
Yeah, so on the front side of that, yeah, that's pretty darn good. That's a nice pattern at 5 degrees. Okay, so now that's what you look like for an end fed. We can run random wire. Random wire, of course, your SWR is all over the place because you're using a 9-to-1 and you're feeding it at the end, and so you really have to have a tuner to tune those in. We're not going to deal with that right now. So let's talk about loops real quick. Just do a new one now. Okay. So Walt and I both run horizontal loops. Okay. And he feeds his 2.5 to 1 balun. I feed mine 2.5 to 1 balun. So we know our setup is going to be 125 ohms there because 2.5 times 50 is 125 ohms. Again, you can feed it with a, excuse me, with a 4-to-1. When you feed a 4-to-1, the antenna gets a little bit longer. So I know we should be at about, let's see. Let's do, you said you have 40-meter loop, Walt? 299.8 divided by 7.150. Okay, and we want to do that just under 100%. So I'm gonna put 0.095. So I know my distance on that loop's gonna be about 39.83 meters. If divide that by 3, if I'm gonna do a delta loop. So I got 13.28 meters each side. So this gets to be a little bit of a funky thing to draw this thing, but we'll do our best here. All right. So I'm gonna go to draw mode, and I'm gonna come out here, and come up to here. And how long is that? That's 19 meters. That's too long. All right. Yeah, it's 19 meters. I need 13. So let's cut this back here. If I find one, I can find the other ones. Makes it easier. Let's see where we're at here. Length is 17, still too long. I get if I come here. It's 11. Okay. $13.41, close enough for what I want to do here. Okay, I'll go back to draw here. And if I come here, I didn't want to do that. Delete. Delete. Okay. Back to the drawing board. Okay, so now I want to go here to here. And okay, I want to go here to here. That's a little short. That's close. Let's move this point. Zoom this up just a little bit, guys. Be patient with me for a second here.
Curious if you just kind of rough draw it and then go in and do the optimize, if it would fix it for you.
You know, on loops it does some of that, but not as much as you'd like it to do.
Yeah.
It tends to give you a kind of a goofy shape, but for right
I
now,
can see that.
let's go with this. Let's see. Why is it? Oh, Jesus. I know what I did. I need to rotate this around the Z axis 90 degrees. No. Around the X axis, I need to rotate it 90 degrees. No. Y axis. Let's try it that way. Well, process of elimination, right? There we go. That's what I wanted. Okay, so now I got this thing laying on the ground. And we're going to get a geometry. I'm going to feed point this one at the beginning of the wire. Feed in the corner, okay? And we're going to go to calculate. We're going to stick this thing. How high in the air do you have yours, Walt?
It's about 20 feet.
All right. So put it at 7 meters. Okay.
That's close. Yeah.
Okay. And let's look at it at 40, the first fundamental, or the fundamental frequency. Our SWR is a little bit. Let's optimize it real quick. Let's let it just figure it out for us, right? Okay. Let's see what it looks like. Oh, darn it. I forget every time you do that. It wants me to come over here and change something. Where's the mouse out? There it is. Cancel. All right. Now let's look at it. Okay. It changed it. Okay. It's got the currents up there. Put the currents back down. All right. So calculate. All right. So SWR is 1.5 to 1. We got good gain here, depending on where that gain's at, right? So let's
Yeah.
look at the far field plot. And because we're so close to the ground, it's going to be kind of a cloud warmer. Look at it in 3D. All right. right, so that's kind of what we're looking at. It just kind of gives us right out the center of that bottom. It's just a big egg right along the long axis of the antenna. Okay.
Mhm.
But if we change this now and go to a different frequency, right? Because we can go down to 20 meters on these things. SWR changed a little bit. Let's look at the far field plot. All right, so now we're starting to flatten out a little bit, and it's giving us a couple different lobes there. Okay. And again, we can take this down to 15 meters as well. All right, start and look at the far field plot. And again, it starts to clock what I call clock face out on you, starting to get multiple lobes, right? And it flattens out, it pancakes out, so your radiation angle starts to drop on these things, right? So if we look at it here, our radiation angle here is about 20 degrees. You know, that's pretty good for short haul DX, right?
Yep.
And if we take this down to 5, elevation at 5 degrees, the magic number as you call it, Danny, right? Yeah, I'm 2.4 dB a gain here, right?
Yep.
Negative 5.7. Here's your highest gain point. So I'm 3 dB better than a standard vertical on 20 meters. So, but that's, you know, those are the basics of using the program. Did everybody kind of get that? I mean, we're an hour and a half almost. So, is everybody happy to get what they wanted out of this for tonight? Or do I
Yeah.
need to do something else?
Nope, that's good.
No, that's good.
I'm
Thanks,
happy.
John.
What I find the program really good for is if you can't run your antenna at the optimal pattern. So let's say you're running an infed half wave and you can't run a standard sloper. Maybe you need to go up a ways and then over. You can plug it into the program and see what your radiation pattern is going to be.
Yeah. So if you did an NFED and you went up and did an inverted V, right?
Yeah.
You can plug that in and say, okay, approximately I'm going to go up over 60 feet. I'm going to put it at 30 feet in the tree and I'm going to drop it another, whatever, 20 feet down. And it'll give you an approximation what your pattern will look like. Now, is that the true pattern? Who knows, right? Until you get out there with a couple field strength meters and spend half a day out there setting it up to see what you're going to do, you won't really know, but you can get an idea of what it's going to look like, what it's going to do. So again, it's one of those things you can learn about how it's going to radiate. You can try it before you build it or before you put it up. You can refine the design, right? So you can make changes to it in the software and then change it out in the field. And then it's fun, right? I don't know about you, but I enjoy doing this kind of stuff. Do you guys? I mean,
Yeah, I
I
like
just
getting on there and playing around with it. It
yeah,
saves you a lot of time too. If you just gives you a little better idea of what you're going to be up against when you do go out in the field or out in your backyard or whatever, and
yeah,
start save you some cutting and fussing around with it.
yeah,
It does me anyway.
yeah. Anybody have any questions?
Uh, let's see if I'm in. Yeah, I'm in here. Does this program save the antenna as a text file or some kind of file that you can
It's
edit, or is it its own proprietary format?
you can let me look at it real quick, Bruce. I'll tell you, I know it saves it as a proprietary file, but let me see if I do a save as. It doesn't give me any other options. I know you can output like the data from the geometry and stuff from it, but I don't think you can change. Yeah, it only saves it as an MAA file. So the base file, but you can output the geometry, you can output you can PDF the radiation patterns, you can JPEG out the 3D radiation pattern. The SWR curves are printable. So if I go to calculate and go to the plots, yeah, you can print out your plots, any of your plots, your far fields, any of that stuff. You can all print all that out, your setup. All that can be output. But again, the file itself that you have the antenna inside of it is going to be a .MAA file. It's proprietary to software only. Does that make sense, Bruce?
Yeah, okay. So, kind of the same problem. I use EasyNeck, which has been around for about 10 years. I've been through a
Right.
couple upgrades on it.
Yeah.
And one of the problems with it is that you can't get in there and manipulate like with a spreadsheet or some other mathematical tool and then feed it back into the antenna program.
Yeah.
So this sounds like it has that same problem. It is
Yeah, I
much
think
more advanced on the the graphics and things like that seem to be a lot easier to use and fancier than the older program. But other than that, it looks like it might even have the same calculating core
it
inside.
does. It does. They're basically the same cores. Easy Neck, MMANA, and 4NEC 2. All three of those have the same cores. Now, there's another piece of software out. You joined a little bit later called SimNEC or SimNEC, which is a newer one. It's been out for just a couple years. I'm still learning it, and it's got a different calculating core in it. It's pretty cool. So if you look up SIMNEC, you can find it and download it. It's pretty cool. So, but anyways, anybody else have any questions? Well, great. Well, thank you guys for being here tonight. I really do appreciate it. Hopefully I didn't bore your pants off. I didn't see anybody sleeping. So, of course, Wayne wasn't there. So, he's probably napping in his chair by now. Because every time we have a meeting, I catch him napping on the Zoom meeting. But thank you all for coming. Next month on the 27th of March, Danny will be doing a presentation on kit building. And unfortunately, I may or may not be there because I'm going to be in Ohio for a wedding that weekend. So if not, if Danny, were you planning to do that at your place or at the clubhouse?
I'll probably just do it here.
Okay. All right. So we'll just maybe take that one 100% vertical or 100% virtual, not vertical, virtual, and do it that way. That'll be easier. That way, Danny, I'll give you the host duties on it. You can start it up and run it from there. Just don't forget to record it and send me the file so we can upload it. All right.
Hit the record button, right?
Yep.
Yeah.
Okay.
All right, guys.
All right.
Everybody have a good night. Thanks, everybody. 7-3 all.
Thanks, John.